Assalamu alaikum. Welcome to the next lecture. In this lecture, we'll be continuing with the grading of cables. So, in the previous class, we have discussed about one of the methods of grading the cables. Today, we'll discuss the second method, that is the intersheath grading. What we do in this case, we use the same homogeneous material, which is made out of the same material. So, having the same permittivity and the dielectric constant, and same dielectric stress. You can see these are the metallic sheets. Here two metallic sheets have been used. One is here and is here, and they are forced to be at a different potential by this transformer, auxiliary transformer. This is kept at potential V, which is actually the actual voltage of this conductor. This is kept at potential V2 because it's connected to this tapping of the transformer, and this is kept at potential V1 with respect to this sheet, that is the ground. So this is how we force the voltage of different metal sheets at different values. So you can see this material, the part of this material whose radius is R2 minus R1, or whose thickness is R2 minus R1, will be at a potential of V minus V2. And similarly for this case, the thickness of this, that is uh, R minus R2, its potential will be it will be stressed with V2 minus V1. Similarly for this case, which is from here to here, this thickness, its potential will be V1 minus 0, that is V1. So with this keeping in mind, we will see how this kind of intersheath grading behaves, and we'll try to ensure and make you understand that the gradient with intersheath will be smaller as compared to the gradient without intersheath. So let's first try to do one thing, that will assume that the thickness are related to each other like this, that is R1 by R is equal to R2 by R1 is equal to R by R2, and their ratio will be same, and let us call it to be equal to alpha. And if you multiply these ratios, you can see from here I have written it again separately over here, that is if you multiply R1 by R multiplied by R2 by R1 multiplied by R by R2. So in this case, this R and R will cancel out, R2 and R2 will be cancelled out, it comes out to be R by R. Since this is alpha, this is also alpha, this is also alpha, it will come out to be alpha cube. That means we can calculate directly alpha. Alpha will be equal to cube root of capital R, that is the radius of overall radius of the cable, divided by the small r, that is the core radius or conductor radius. So with this arrangement, that is this arrangement, the gradient at the surface of the conductor, that is the gradient at this conductor, will be, we have to look this cable as if its thickness is only this from R to R1. So that means and voltage across this will be V minus V2. So this G max in this case will be equal to V minus V2 divided by R ln of R1 by R, because we are only considering this portion, this thickness, that is from R to R1. That's what we get this relation. Actually, we have used this equation. Earlier, we were having this type of a cable where the G max was V is the total operating voltage, R is the conductor radius, R is the radius of the cable. So when we find out G max from this point to this point, so it comes out to be this. So here our interested area or our interested thickness is only from R to R1. So we have to find out the voltage between R and R1, and also the distances will be from R to R1. That is why this equation will be like this. So it has been derived from this. The voltage appearing is V minus V2, and this starting point is R and ending point is R1 in this case. So here it was, ending point was capital R. So this is the voltage at the surface of the conductor. Similarly, gradient at the surface of the conductor. Similarly, gradient at the radii R1 and R2 will respectively be. So that means from here R1 to R2, that is from this distance to this distance. So from this distance to this distance, you will see the voltage is V2 minus V1, V2 minus V1. Starting point is this R1, that is here it is R1, and ending point is R2. So it comes out to be V2 minus V1 divided by R1 ln of R2 by R1. Similarly, For the third one, here voltage will be V1 minus 0, that is V1. So the distance will be from R2 to capital R. So here it will be R2 ln of capital R by R2. These are the three voltage equations, and since we are using the same homogeneous material, these three equations will be equal. So that means V minus V2 is equal to V minus V2 divided by R ln of R1 by R is equal to V2 minus V1 divided by R1 ln of R2 by R is equal to V1 divided by R2 ln of R by uh, R2. It is not minus over here, it is simply V1 divided by this. So since we know that R1 by R is equal to R2 by R1 is equal to R by R2 is equal to alpha, so it will be equal to R ln of alpha, R1 ln of alpha, R2 ln of alpha. This ln of alpha, ln of alpha, ln of alpha will cancel out. It comes out to be simplified this equation. So here we want to compare the gradients under the two conditions. Therefore, we must express the terms of V, R, and alpha. To find the gradient with intersheath, we express V1 and V2 in terms of V1 in terms of V2 and then V2 in terms of V. So here we get V1 in terms of V2 by equating these two equations, that is this equation and this equation, or this equation and this equation, we get V1 in terms of V2. So when we get that V1 in terms of V2, we get this. Now to express V2 in terms of V, so from this equation, V2 in terms of V, we will use this equation and this equation. That is V minus V2 is equal divided by R is equal to V2 minus V1 divided by this R1, and putting the value of V1 in terms of V2, we get this equation. So finally, by substituting this V2 in terms V1 in terms of V2, we get finally V2 is equal to V into alpha 1 plus into 1 plus alpha divided by 1 plus alpha square. Now substituting the V2 in the equation is 9.9. So we get, that is this equation. This equation we get G max. So V minus V2 divided by R ln of alpha, you can see from here. V minus V2 divided by ln of R ln of alpha, this will remain as it is. We have to put the value of V2 in terms of V. So V2 in terms of V will be this. So wait a minute, yes, this is this. So V2 in terms of V will be like this. So it comes out to be this. And finally, this will be V ln of V R ln of alpha into 1 divided by 1 plus alpha square, 1 plus alpha square. So this is the final G max with intersheath. So without intersheath, we know that the gradient is V divided by R ln of R by R. This is from this equation. That is this. Without intersheath, this system will look like this, and G max will be equal to V divided by R ln of R by R. Here I have not used the G max just to make you understand that this G is again the G max without intersheaths, and this G max is with intersheaths. So I have not used here G max, otherwise it is the G max without intersheaths. So this G will be equal to V divided by R ln of R by R, but this R by R, as we know, is equal to alpha cube, and this will be R ln of alpha cube. That cube will be multiplied to this. It will be equal to 3R ln of alpha. So this is the value of the gradient without intersheath. So G max by G, that means we need to divide this equation by this equation. You can see it comes out to be 3 divided by 1 plus alpha square. From the geometry of the cable, as we know, R alpha is equal to R1 by R, which will be greater than 1 because R1 is greater than R small r, and similarly R2 by R1 is also equal to this alpha. It is also greater than 1 because R2 is greater than R1. Similarly, R divided by R2, that's also greater than 1. So this term, you will see that the gradient, this will be greater than 3, and this is greater than 3. So this portion will be this less than 1. When this is less than 1, that means G max will be less than G. So that means the gradient with intersheath is lower than without intersheath for same overall size and operating voltage of the cable. This is what we intend to prove. This means that a cable of a particular size can be operated for higher voltages, or for a particular voltage size of the cable can be reduced. So the voltage of the cable with this intersheath arranged is given by, the voltage will be given by G max R ln of R1 by R plus R1 ln of R2 by R1 plus R2 ln of R by R2. This is the total voltage, and since we know this is alpha ln of alpha ln of alpha, it comes out and it will be equal to G max ln of alpha R1 plus R2 plus R. So this is the total voltage, and the gradient for this case will be less as compared to without intersheaths. Now let us try to do, okay. There can be other elements of the intersheath as well. The insulating material thickness between the successive intersheaths is constant. If that is the case, then R1 is equal to R plus D. If D is the constant thickness between the different intersheaths, then R2 will be equal to R plus 2D, and similarly R will be equal to R plus 3D, where D is the constant thickness between the intersheaths. Now we will use the similar example. A 66 kV concentric cable with two intersheaths has core diameter of 1.8 centimeter. Determine dielectric material 3.5 mm thick constitutes the three zones of insulation. That means here dielectric material having thickness 3.5 has the constant thickness D 3.5. Determine the maximum stress in each of the three layers if 20 kV is maintained across each of the inner two. That means this V1 by V minus V1 is equal to 20 kV, and V1 minus V2 is equal to 20 kV. Here this connection is up to this only, this V1 is not connected to this V is connected to this conductor, it is at potential of the conductor, but this V is connected over here and V2 is exactly connected here, and this is the ground potential that is here shown. So keeping these things in our mind, first we'll calculate the total thickness of the total diameter of the cable, that will be this 0.5 plus this 3.5 plus 3.5 plus 3.5, so it comes out to be 0.9 plus 3 into 0.35, it comes out to be 1.9, and this is the overall radius of the cable. So G1 max will be the maximum stress on the surface of the conductor, G2 max will be the maximum stress on the first intersheath, G3 max will be the maximum stress on the second intersheath. So we know that this G2 max will be equal to V1 minus V2 divided by R1 ln of R2 by R1, or V1 minus V2 is equal to G2 max R1 ln of R2 by R1. Here this is not the constant thing. In the previous case we assumed that G1, G2 and G3 are the constant. So here it is given that the two intersheaths have a potential of 20 kV. So this comes out to be equal to, when you put the value of R1 and ln of R2 by R1, it comes out to be 0.3085. G2 max, it is equal to 20 kV. Similarly, V minus V2 is equal to G1 R ln of R1 by R. This is G1 max into 0.9, that's this value, and 1.25 divided by this 0.9, it comes out to be this value, 0.2956 G1. It's also equal to 20. So V2, that is this voltage, V2 will be equal to G3 R2 ln of R3 by R2, which comes out to be 0.3165 G3 max. So since from here it is this value is equal to 20, that means G1 max is equal to 20 divided by this 0.2956, it's coming out to be 67.6 kV per centimeter. So V1 minus V2, which is 20 kV, that is this, is equal to 0.3085 G2. So G2 is equal to 20 divided by 0.3085, it comes out to be 64.83 kV per centimeter. We would have calculated G2 max here also, because here the equation and here the equation is same. So V2, that is 66 minus 40, that is 26 kV. It is not the same, because the total operating voltage of the cable is 66 and the 40 volt is appearing between these two, that is V minus V1 and V2 minus V1. The rest will appear between these. So this comes out to be 26 kV. So putting the value of G3 over here, so V2, that is G3 will be equal to 26 divided by 0.3165, it comes out to be 82 kilovolt per centimeter. This is how you can calculate the G3 max, or sometimes you may be asked, you may be given the value of this maximum stress and you are asked to find out the different voltages. You can use the same formula to calculate that. Okay. Now coming to the other topic, that is the heating of cables. As we know that the temperature rise of the body depends upon the heat generation and the heat dissipation. If the heat generation is more than the heat dissipation, body will be heated, or if the heat generation is less than heat dissipated, body will get cool. So in case of underground cable, there are three sources of heat. That is the core loss, it's actually the conductor loss, it's copper loss in the core cable, it will be I square R loss. The dielectric loss, that is the loss in the dielectric, and the sheath loss in the sheath due to the eddy currents. So and the heat in and finally the heat will be dissipated in the atmosphere. Core loss. The first will be discussed is the core loss. In order to find out the core loss value of the resistance of the cable is calculated as follows. Knowing the resistance of the conductor at ambient temperature, usually we know the resistance of the conductor, usually aluminum and this copper at 20 degrees centigrade. We can calculate its temperature at any temperature. Sorry, calculate the resistance of the copper or aluminum at any temperature, and we also know its value of temperature coefficient, that's alpha. So we can find out this at any temperature. So where alpha is the temperature coefficient of the conductor material and T is the difference in the temperature, in which temperature, which in this case is T is equal to 65 minus 25, that's 45. If we have to calculate the value of the resistance of the conductor at 65 degrees centigrade. One more thing, since the effective area of the section cable is smaller than the actual physical section, the effective resistance of the cable is larger. A factor of 1.02 is multiplied to get this resistance. This is an empirical formula. The length of the outermost strand is greater than the central strand. I have discussed it in the class previously. The effect of the stranding on the resistance is obtained by multiplying the resistance as calculated according to the length of the central strand by a factor of 1.02. Here also 1.02 is multiplied. Having calculated the resistance of the cable, the core loss is then calculated by simply multiplying this resistance by I square. So we get the uh, core loss of the conductors. Now the second one is the dielectric loss. The cable usually is a sort of a capacitor with the core and the sheath forming the two plates of the condenser separated by the dielectric material. We have already discussed it. The equivalent circuit for this system is represented by a parallel combination of a leakage resistance R and a capacitance C. Usually, ideally, we would have represented this cable by a simple capacitance, because conductor is one plate and sheath is another plate, and dielectric is dielectric material of the cable will act as the dielectric of the capacitor. But because of its loss which is present in the dielectric, so we have to also represent that loss by resistance. As I have told you in the earlier classes, that we usually represent losses always in resistance, and here we use this resistance, or we represent this loss as a parallel resistance with this capacitance, as we have done in case of the transformer. So in this case, this will have a very high value. For practical capacitance, this IR will be very small, so we can see ideally this IR can be neglected and we can replace or represent this capacitance or cable by a simple capacitor. But practically there is some value of this IR. This cable will not be ideal and there will be some dielectric loss. We have to represent it by this. So that P square, or P is equal to this V square by R. V is the operating voltage of the cable and R is the resistance, leakage resistance. So, or it is also known as the insulation resistance. So this can be calculated, this P square can be calculated by having different values, by not because this insulation resistance is sometimes not given or difficult to calculate, but this delta is actually the inherent of the cable. It is usually given in the data sheet, so by using that value you can calculate this P in the normal operating conditions. So let us say this is voltage V. We can use this phasor diagram to calculate this. This is phasor V, and this current will be in this in phase with this voltage. That is, this current IR will be equal to V by R. It will be in phase with V. This IC will be leading to this V by 90 degree. This IC will be like this, with this 90 degree. This IC will be equal to V omega C. So I will be the phasor sum of this IC and this IR. This phi is the power factor angle of this cable, because this I is leading in this case to V by phi, and this will be the power factor angle, and this is the delta angle, that is the difference of the between IC and the actual I. So for our ideal condition, this delta will be 0 and IC and I will be coincident, they will be collinear, we can say. This IR will be equal to 0. So for cable, for a good cable, this delta should be very close to 0 and this I should be very close, equal to, very close to the value of the IC, and they should be considered. So from the geometry you can see this delta and this phi should be will be equal to 90 degrees, and this phi will be equal to 90 minus delta. Now From the phasor diagram, this V by R tan delta, that is this, will be equal to perpendicular divided by base. Perpendicular will be this perpendicular will be V by R, and this base will be V omega C. So that means V by R will be equal to V omega C tan of delta. Multiplying V on both sides, it will be V square R, which is equal to P, that is equal to V square omega C tan delta, will be the power loss that is given by this cable. So from the phasor diagram, the power factor angle of the dielectric is given by this phi is equal to 90 minus delta, that is from here, and power factor will be cos of phi will be equal to cos of 90 minus delta, that will be sine delta. Cos of phi will be equal to sine of delta. So let us try to do one numerical on this. It's very simple. A 3-phase 33 kV 50 Hz 3-core cable has a capacitance of 19.5 microfarad. Find the dielectric loss per phase if the power factor of the unloaded cable is 0.08. So power factor is cos phi 0.08, phi is equal to 85.41, that is the cos inverse of 0.08. Delta is equal to 90 minus phi, that is 4.588. So PL, that is the power loss, is equal to V square omega C tan delta, that is this will be the phase voltage. This is equal to 33,000 divided by root 3 whole square into 2 pi into 50, that is omega, and this is the value of C. This is tan delta divided by 100, just to convert into kilowatt. It comes out to be 178.45 kilowatt per phase. This was about cables. Now let us move to the neutral grounding. So one of the important aspect of the power system, the neutral grounding. And in this case, when we design a power system, based on this, we can analyze the performance of the short circuit. We can analyze the performance of stability, and we have a lot of analysis in case of protection. And when we do that, this neutral grounding has uh, a great role to play in these topics, that is short circuit analysis, stability analysis, and power system protection. In most of the modern high voltage systems, the neutral of the system is solidly grounded. That means directly the neutral of the system is directly connected to the ground by a simple wire without any intentional impedance between the neutral and the ground. Usually neutral is the neutral point of the star of the generator or the transformer, and ground is the earth, or we can say soil. So usually the neutral is usually connected to the ground. That means when neutral point, there is a connection between the neutral point and the soil, and how that soil is the ground point of the power system is slightly different from the normal soil or normal ground. So for the time being, you keep in your mind that the ground is the same soil that we have around us. Generally, the neutral of the generator is connected through the resistance to limit the stator short circuit current, and also for the stability reasons. You'll always see that generator will be, synchronous generator particularly, will be connected to the ground to a resistance. So it is for the purpose to reduce the short circuit current and for the improvement of the stability reasons. So this is not a solidly grounded system, this is a resistance grounded system. Now this is just broad definition of the neutral grounding and broad overview of the neutral grounding, how this is done. Now what are the different advantages of the neutral grounding? So the first one is voltages of the phases are limited to the phase to ground voltages. In case of the isolated grounding, you will see that we'll also discuss that the phase voltages are not at the phase voltage, they will be at the line voltages. So when we do the neutral grounding, the phase voltages will remain at the phase voltages. So in case of isolated grounding, you will see there will be arcing grounding and there will be transient line to ground faults, which are absent in case of neutral grounding. So when neutral grounding is used, protective relays can be used to protect the system against line to ground faults, and the over voltage due to lighting and due to switching will be discharged to ground through this neutral. Otherwise, there will be a positive reflection at the isolated neutral grounding of the system. Isolated neutral of the system means when the neutral is not connected to the ground. That means when the neutral is not connected to the soil. One more important aspect of the grounding is that it ensures safety of the life and property from the hazards of electrical shocks and fires. So these are the different advantages, and because of these, we are very much helpless to go for the neutral grounding. So there are some disadvantages, but they are not much so that we can go for the isolated ground, but you should also know that it is possible to maintain the supply with fault on one line. If there occurs a fault on one line, since there is no path for the current to flow, it will act as an open circuit. Other two circuits will still continue to supply, but at the higher voltages. And in case of isolated neutral, there will be no zero sequence currents. You will also will get this. There will be zero sequence currents in case of neutral grounding, and in case of isolated ground there will be no zero sequence current, and because of this zero sequence current there will be communication interference. So isolated neutral, there will be no communication interference. Now there are usually we have usually broadly classified this grounding into two types. One is earthing and another is grounding. So just to make you sure, otherwise in broader aspect uh, they are generally defined to be same, but for your sake of understanding I have separated them into two types. One is earthing or equipment grounding. In this case, what we do, the process of connecting the metallic frame, that is the non-current carrying part, which does not carry current, of electrical equipment to earth is called the earthing. So that means earth means the soil. So in this case, usually we try to connect the equipment frame or equipment casing to the earth or to the soil. In this case, there is not any live part which is connected to the ground. The second one is grounding or neutral grounding. This process involves the connecting some electrical part of the system, for example, neutral point in a star connected system. One conductor or the secondary of the transformer, they will be connected to the earth or soil. This type of grounding is known as neutral grounding. So that is how they have been differentiated. One more thing that is to be kept in mind, if grounding is done systematically in the line of power system, we can effectively prevent accidents and damage to the equipment or the power system, and at the same time we can maintain the continuity of the supply to the consumers. This is very important. So let us try to have a little insight about the earthing. Equipment grounding or the earthing. This is again the same definition. The process of connecting the non-current carrying part, that is the metallic enclosure or casing of the electrical equipment to earth, that is soil, in such a way that in case of insulation failure, the enclosure effectively remains at earth potential, is called equipment grounding. Let us see how it remains at the earth potential. So in the interest of easy understanding, we shall divide the discussion into three heads. One is the ungrounded enclosure, another is the enclosure connected to the neutral wire, and another is the ground wire connected to enclosure. So this is the one case in which we have the supply. This is the line, this is the switch, this is, let us say, an electrical motor. For the time you this is actually the fictitious resistance between the motor and its casing. It is in normal case it is of the order of very mega ohms or giga ohms. So that means this current will be zero. So normally if a person touches this casing, there will be no current flowing through this because the value of this Re will be very high. There is no any insulation failure between this motor and the ground. And in case of abnormal condition, when this insulation fails, you'll see this Re becomes very small. And since when this person touches to this casing, this may be at this potential, at the line potential, and the person whose feet are at the ground, there will be a current flowing through this path and through his body, and it may be quite dangerous for the person, and it may result in his death. So to avoid this, one procedure is to connect this casing to this neutral wire. So in this case, if in case of abnormal condition, this casing is at the live potential because of the insulation failure of this motor. So in this case, the path becomes like this because the path would have been this also. Since resistance of the person is of the order of kilo ohms, you will see it will follow this path. So in that case, the person is safeguarded. But sometimes this may also uh, be fatal for a person because of this configuration. If the switch is installed in the neutral wire because of some confusion, in this case you will see that when abnormal condition occurs, insulation breakdown occurs, this Re becomes very small. There will be this point will be again at the live potential, there is no path through this, it has no choice to flow through the body of the person. So in that case also it will be very dangerous. So to avoid these things, both the cases, we use a third wire that's known as ground wire, and ground wires will be connected directly to the casing. You can see even if the switch is on the neutral wire or on the line, and if we have a abnormal condition, the path will always be like this. So that is why you will always see this ground potential or ground wire, which is usually uh, colored in green, that will always be connected to the casing just to avoid such type of faults or such type of hazards for the person. So this is very important. This is known as equipment, and this is the importance of the equipment grounding, or we can say earthing. So a simple system grounding, but this is in regard to the protection of the personnel. You can see that when this is the transformer primary, this is the transformer secondary. In normal condition, there will be a capacitance formed between the primary and secondary, and there will be another capacitance formed between this secondary and the ground. If this point is not connected to ground, there will be some voltage developed with this point 2 with respect to ground because of this capacitance. So when a normal person touches this point, that is 2 point, or even 1 point, you will see a lot of current will flow through the person, and it will result in the instant death of the person. Now in case of system grounding, you can see from here, in case of system grounding, if this point is grounded, I have not shown that figure over here. So this point, which is at a potential of 5000 in ungrounded system, it will be at a zero potential. Now if a person touches this point, you'll see he will be safe. He'll be touching a potential of 0 volt. But in case of this, if he touches this, he will be having a potential of 230 volt. He will get a shock. But when he touches the point 2, he will be very safe. Similarly, when a fault occurs, you'll see the high voltage will be directly connected to this point, and in case of ungrounded system, even a person connected to this point or this point, he will be in danger and he will die instantaneously. But in case of grounded system, you will see the path of the current will be this, not through this or not through a person, and in this case a person will be safeguarded. For the time being, I will stop here. Thank you.